Imagine a single, highly charged particle locked at the origin. It generates an electrostatic field that permeates the surrounding space. Pushing another object into that field requires an external force. This is analogous to compressing a physical spring or lifting a weight against gravity. Work performed against these conservative forces is preserved within the system as potential energy. The Coulomb force, the repulsion or attraction between charges, is also conservative. This allows us to map the potential energy for any charge introduced into an electrostatic field. To create a universal standard for this map, we use a unit positive test charge. This is a theoretical probe so small that it measures the energy at a point without disturbing the source charge at the origin. Dividing the total work by the magnitude of this test charge yields a value that remains consistent regardless of the probe's own size. This resulting quantity is the electrostatic potential, denoted as V. Electric potential provides a scalar map of the environment. It assigns a specific energy value to every coordinate, representing the energy cost of occupying that position relative to the source. Defining absolute potential requires a reference point where the value is 0. Because the influence of an electric field only vanishes at an infinite distance, we must set our baseline at infinity. Since the electrostatic force is conservative, the total work remains identical regardless of the route taken. A test charge can follow a straight, zigzagged, or looping path from infinity to point P without changing the energy required. For the purpose of derivation, we select the most direct route, a straight radial line moving inward from infinity toward our target distance, r. This radial path facilitates the derivation. By calculating the work along this trajectory, we define the potential at any distance r for any point in the system. We begin with source charge q at the origin, and our destination, point P, at distance r. We track our test charge as it approaches an intermediate position, r'. At this location, the electric field exerts an outward force. To continue moving the charge inward without acceleration, our external force must exert an equal and opposite push. Because the repulsive force intensifies as we approach the origin, the total work must be calculated in microscopic segments. We measure the work required for an infinitesimal displacement, dr'. This tiny increment of work is the product of force and displacement. A negative sign appears in the expression because our inward displacement moves against the direction of the outward electric force. The total potential is the sum of these infinite microscopic steps. We use integration to transition from these individual bits of work to a complete mathematical derivation. We establish an integral for the total work, evaluating the function from the starting boundary at infinity down to our destination at distance r. Integrating the inverse square term with respect to r' transforms the expression into -1 over r'. When we substitute our limits, the upper boundary gives us the value at distance r. The lower boundary at infinity resolves to 0, removing that term from the calculation entirely. The final potential at distance r is the charge q divided by 4 pi epsilon naught r. This result defines the electrical landscape at every coordinate. By entering the distance from the source, we determine the exact energy required to bring a charge to that point. The formula for electric potential follows a 1 over r relationship. This is a key distinction from the electric field, which diminishes much more rapidly at a rate of 1 over r squared. This graph illustrates how the properties diverge. The electric field curve drops sharply, while the potential curve descends gradually. At large distances, the immediate force is minimal, but potential remains high, representing the accumulated energy from the entire journey. The field describes local force, but potential reflects a cumulative property. It accounts for the work performed throughout the path from infinity to the current coordinate. In summary, electrostatic potential is the work done per unit charge in bringing a test charge from infinity to a point without acceleration. Because potential is a scalar quantity, determining the topography of a multi-charge system is straightforward. We calculate the values for each charge independently and sum them to find the total potential. The diverse interactions of an electric field condense into a calculation of the energy requirements at a specific point, expressed through the formula V equals Q over 4 pi epsilon naught R.